Hey, any questions about anything? Yes? Rohit? Okay. Yeah. What happened on my thumb? Well, you know those old style storm windows with the 2 glass panes in the screening? Okay. So I was changing one of those on Friday night. I pushed the screen up and I pulled the window down and I was sort of wrestling to get it to go in its little holes. And the screen came crashing down like a guillotine and crushed my thumbs. Okay. Not once, but twice. Okay. And the right one was really hurting. And so Saturday, I had a lot of stuff to do, and I went to the hockey game, and after the hockey game, it was really swollen and felt really weird, and I thought, well, I'm not going to go to the ER on Saturday night. That's when all the crazies are there. It takes 5 hours to get out. So I went Sunday morning to the convenient care center. Yes, it's broken. I have what's called a tuft fracture of my distal phalanx on my right thumb. They gave me this little splint, and I don't even really have to wear it. And I don't know how it's going to work writing on the board, but all I can say is that in 1994, before most of you were born, I actually, at the very end of the semester, I injured this thumb worse. You know, I tore a ligament and broke a bone down here. I had a cast that went all the way up to here and all the way up to here. And I gave the last 2 lectures holding the chalk between these 2 fingers. So I am able to do that if necessary, but I'm hoping it won't be necessary. Any other questions? Okay, the takeaway from that is don't change your storm windows when it's dark outside, because you need to see the details of what's going on up top. You need to see why the screen isn't feeling quite like it's insecure. You know, it was going up the wrong hole. Like I could see that the next morning. It was like, oh, duh. You know, well, if I'd only known that last night, I wouldn't have done this. So I advise against changing your storm windows late at night. Any other questions? Okay. By the way, thank you for all getting promptly back to me about homework 6. I'm learning that more people than I thought were pretty behind in the homeworks, and so I'm going to try to really nudge you to try to catch up, because, I mean, it's basically, you'll make your own life easier if you try to stay a little more caught up.
When is homework 7?
Homework 7? I'm about to send out a message if you haven't hinted at homework 7, so, you know. But basically, the solutions to 6 are going to go up tomorrow about noon, based on everyone's responses. And, you know, for those of you who did it on time, awesome, congratulations. You've been able to take it easy while other people didn't. But anyway, that's what's going on with that. So I'm not sure. I haven't decided. But just remember, in a few weeks, we're going to have a prelim. And so as we get closer to that, we're going to have closer hard deadlines. Yeah.
Well, in 3100, like, they're doing, like, Laplace transforms, and I kind of get that, like, you're pretty much doing similar thing with, like, Fourier transforms, but, like, I'm not really understanding why there's 2 of those things. Like, what's the difference between the 2?
The difference between Fourier and Laplace transforms, and I don't know whether you're doing one-sided or two-sided Laplace transforms in 3100. Do you go from 0 to infinity or minus infinity to infinity?
Minus infinity.
Okay, two-sided. Basically, what's going on there is that the Laplace transform applies to a more general class of signals. Like, you could have something that starts at time 0 and grows exponentially to infinity. That's going to have a Laplace transform, but it won't have a Fourier transform. But for signals that have Fourier transforms, their Laplace transform, if you evaluate it at s equals j omega, you get the Fourier transform. So they are related closely.
So Laplace transform is kind of like a general form of Fourier transform?
It's kind of like that, but not quite. It's a little more complicated, you know, because we allow for deltas in frequency, and Laplace is never going to have any deltas in the S domain. But yeah, if we have time this semester, we'll get to Laplace a little bit. There's going to be a chapter in the monograph on it, but there isn't yet. Think of Laplace. Laplace transform is like the continuous time version. I'll get it. Why? You don't want me to touch your pen? think of the Laplace transform is a continuous time version of the Z transform.
Okay.
The Fourier transform is a continuous time version of the discrete time Fourier transform, which is the next thing we're going to talk about after wavelets. Okay, so anyway, good question. Glad to see you're linking your courses together.
Oh.
Anything else? All right, well, today I'm hoping to wrap up this very brief introduction to wavelets and everything. And wait, Dan, did you want to tell me to Google something? No, okay. It was more of a hallway kind of thing. Yeah. Okay. All right, so I'm just going to see how this goes with this splint on my finger. I'm not sure. Yeah, it is. Have to find a comfortable way to do this. Okay, so we're talking about wavelets, and specifically, we were talking about the Haar wavelet system. And for the Haar wavelet system, you had this function, the mother wavelet, psi has specification psi of t is equal to 1 when t is between 0 and 1 and 0 otherwise. So it looks like this versus t. Actually, no, minus 1 over this range. So this is what psi of t looks like versus t. Okay, 0 before time 0, after time 1, and it goes down to minus 1 and goes up to plus 1. And remember, for a wavelet system, what does it mean for the thing to be in the mother wavelet? It means that the set of all psi and k, such that n and k are integers, is a complete orthonormal set. I think I'm going to take this thing off, see how it goes. Don't worry, it's not green and purple anymore. All right. This is a complete orthonormal set in L2, where psi and k is equal to scale sub 2 to the k shift sub n of psi. And we talked at length last time about what these things look like for various values of n and k. Psi n k is going to be a little replica of that thing, of a different, oh, and I always forget the opening factor here, 2 to the k over 2 out front. It's going to look like, for different values of n and k, either a dilated or a crunched in version of this thing with appropriate height to make it have unit norm in L2. And psi n k is going to be local around time n times 2 to the minus k. Okay, so it's only going to have activity there. And so the coefficients, if you're given x and L2, the coefficients x inner product with psi n k, the set of all those coefficients as n and k run over the integers, are what we call the Haar wavelet coefficients. Of x. And if you think of graphing them in a grayscale or whatever, with n times 2 to the minus k on one axis and k or 2 to the k on the other axis, it gives you sort of a pictorial representation. I went over this a little bit last time, of the activity in the signal x at various times at various scales. Okay, so this is what people might call the Haar wavelet transform of x. It's the set of coefficients. I'm not going to name it officially. I'm just going to say those are the things we look for when we're doing a Haar wavelet analysis of a given signal x in L2. Yes, Denzel.
For this to work, does it have to be an L2? Like,
Yeah. Yeah.
just because I guess we never kind of prove why it's an L2.
We never what?
Prove why it's an L2 or how it's an L2.
Well, all the size are pretty obviously an L2, right? And we showed last time, I gave you a sketch of a proof of this fact. And the proof of this fact hinged on x being an L2, because you couldn't have something constant in L2 unless it was 0. So that's where L2 came in a sort of incontrovertible way. All right, now, obviously, and this is, Zach raised this point last time, you know, here you are, you're computing a doubly countably infinite set of coefficients. How can that be more efficient in any way than doing anything else we've ever done? Well, I gave you a selling point for this, that it sort of gave you local information about the signal, localized in time and space. That's a good thing, but I didn't sell you on the data compression part of it at all. So today I want to try to sell you on that a little bit. And to do that, what I have to do is talk about a sort of a different way of looking at the Haar wavelet system. And this shows how the Haar wavelet system is a specific example of a more general kind of wavelet system that arises from what's called a multi-resolution analysis of L2. Okay, so that's what I want to talk about for the first half today, roughly. So it turns out that the Haar system is an example. See, what I have to do is I just have to figure out a way of holding the chalk without putting direct pressure on the end of the thumb. Okay, that's the key. So if anyone has, maybe during the break you can come up and give me suggestions. But I'm trying various ways of doing this. If it's illegible or if it's too light, please let me know. So this is an example of a general phenomenon, a general type of wavelet system called a multi-resolution analysis of L2. Okay, now I'm not going to start from square one and say, here's the definition of a multi-resolution analysis. What I'm going to do is I'm going to start defining things about the Haar wavelets, and then at the end of that, I'm going to say anything that has these properties is what we call a multi-resolution analysis. Okay, so first, let phi be the signal. It's a rather simple signal with specification phi of t, and this is the one I wrote by mistake earlier. It's 1 between 0 and 1, and 0 otherwise. So this is what phi of t looks like versus t. It's just like a little pulse of width 1, starting at time 0, ending at time 1. We call phi the scaling function for the Haar system. Why? I don't know. They just call it that. Now what I want to do is, for each k, I'm going to define a subspace of L2. And I'm going to start with V0. V0. So let V0 equal what? This is going to be the set of all signals in L2 that are constant. So this is the set of all signals that are constant on every interval of the form n to n plus 1. And I'm writing the interval that way because that's the way the phi is set up, that's the way the size are set up, and that's the way everybody talks about it, as n runs over the integers. So V0 is a set of step functions. It has steps of width 1 of various heights. And since it has to be an L2, after a while it has to be 0 or going to 0 pretty fast. But anyway, it's a set of step functions. So note, V0 is a set of step functions And all are decent, if you think about it. The only discontinuities in these things are jumps, and the only jumps in these signals happen at integer values of time. Furthermore, V0 is closed under integer shifting. So it's closed under shift sub n for all integers n. So it's not quite closed under shifting. It's closed under integer shifting. And it's also a subspace. These are all these nice properties. It's closed under, so it's a subspace of L2. If you take two step functions whose steps are on these integer intervals and you take a linear combo of them, you get another one. So it's closed under taking linear combos. And in fact, it's a Hilbert space. Using the usual L2 inner product. It's closed under taking of limits in L2. And I'm not going to sit down and prove that exactly, but that's true. And finally, if I take the scaling function, this phi over here, and I take all of its integer shifts, that set forms an orthonormal basis for V0. So the set of all shift sub n of phi for n in the integers, that's a complete orthonormal set in V0. And you can sort of see why. First of all, they are orthonormal. They're obviously orthogonal because if you take an integer shift to phi, its support interval is disjoint from phi. And any two integer shifts with different integers have disjoint support intervals. So it's clear that they are mutually orthogonal. They are normalized. Their integral squared is 1. So it's an orthonormal set. And it's complete because pretty obviously you can express any step function, all of whose steps are on these integer intervals, as a convergent infinite linear combo of those things. Okay, so those are all factoids about V0. Now, in analogy, with the psi sub nk notation, I'm going to do the same thing for the phi. I'm going to set phi sub nk to be equal to 2 to the n over 2 scale sub 2 to the k shift sub n of phi for all n in the integers, n to k. And one thing you might want to note is these things are also orthonormal with each other, and or orthogonal to each other, and they have unit length. So phi nk equals 1 for all n and k normalized. And they're all mutually orthogonal. They're not all mutually orthogonal. So let me save up that statement for a second. All right, so now I'm going to take V0 and I'm going to do the following. For each k in the integers, I'm going to set V sub k equal to shifts or scale sub 2 to the k. So it's the set of all scale sub 2 to the k of little v such that little v is in V0. And if you want, you can write that in sort of a schematic notation as scale sub 2 to the k of V0. Yeah, Will.
On the Wavelet coefficient on B and K, is that 2 to the n over?
2 to the k over 2. Yeah, sorry. No, that's a k. Can't you see? No, just kidding. Yeah, I had it wrong. Thank you. All right. So anyway, for every k, I'm just going to take all the signals in V0 and scale them by 2 to the k. Yes, Manish.
For the set V naught, when you say it's of the form n comma n plus 1, is that for some n or for all n?
It's constant on every interval of that form. So it's constant on the interval 0 to 1. It's constant on the interval 1 to 2. It might be a different value.
Okay.
Constant on the interval 19 to 20. Constant on the interval 10 to the 59th minus 1 to 10 to the 59th.
Okay.
Okay. All right. So anyway, so just take all the v's in V0 and scale them by 2 to the k. And if you think about what you do when you do that, you're taking a step function that's constant on all those intervals, and you're scaling it by 2 to the k. What do you get? You get the set of all signals that are constant on little intervals of length 2 to the minus k. So note, Vk is the set of all signals constant on every interval of the form, not n to n plus 1, but L times 2 to the minus k to L plus 1 times 2 to the minus k. For all L in the integers. So it's a set of step functions. Again, Vk is a set of step functions. It's closed under shift sub what? Well, it's closed under shift sub n, but it's also closed under shift times any multiple of 2 to the k. It's a subspace. In fact, it's a Hilbert space. So let me write down these things. So note, V0 is a subspace of L2, and in fact it's a Hilbert space. And it's closed under shifting by any integer multiple of 2 to the k. So it's closed under shift sub L times 2 to the k, or let's use n here, or n times 2 to the minus k for all n in Z. All right, so that's another property of it. It's a set of step functions again, all the things that are decent, and guess what? The set of all phi sub n k as n runs over the integers is a complete orthonormal set. In V sub k. So really, V sub k is just a scaled version of V0. It has all the same properties as V0, except they're all scaled. Instead of having phi n comma 0, which is the set of all shifts of n of phi as being an orthonormal basis, we have phi n comma k as n runs over the integers to be a complete orthonormal set. All right, so we do this for every k. And here's a major observation. For every k, we have the following containment. Vk is contained in Vk plus 1. Why is this true? Well, let's think about it. What is Vk? Let's do k equals 0. V0 is the set of all things that are constant on every interval of the form 0 to 1, or n to n plus 1. Now, if you're constant on every interval of the point n to n plus 1, you're also constant on the two half subintervals of there, right? N to n plus 1 half, and n plus 1 half to n plus 1. So anytime you're constant on all the unit length intervals that start as integers, you're constant on all the half unit length intervals that start at integers. So that means that V0 is contained in V1. If you're constant on those intervals, you're constant on the ones that are half as long. And you keep going up like that. So what you have, for every k, you have this containment, and therefore you have this nested set of subspaces. Dot, 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 dot. V sub minus 2, contained in V sub minus 1, contained in V0, contained in V1, contained in V2, contained in dot, 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 dot. And that's a nested sequence of subspaces. And it turns out that it's pretty easy to show the intersection of all these things. And I'm going to write this notation that you may or may not be familiar with. Intersection from k equals minus infinity to infinity of the v sub k's is equal to nothing except 0. The only signal that's in all those subspaces is the 0 signal. And you can do a hand-wavy argument for that. The ones in here are constant over unit length intervals. The ones in here are constant over 2 length intervals. These are constant over 3 length intervals, and so on. And anything that's constant over every length interval is going to be constant over all t, and therefore has to be 0 if it's in L2. And they, in some sense, span L2 in the sense that every x in L2 is the limit of a Cauchy sequence. Or let's not even use Cauchy. It's the limit of a sequence of signals in their union. K equals minus infinity to infinity of Vk. So in some sense what we've got is we've got a decomposition of L2 into a nested sequence of subspaces that increase up to L2. And that sequence of subspaces, along with the phi, all of whose integers shift span V0, and along with all those properties, that the scale of all the ones in V0 to the k are in Vk and all that, that's what constitutes being a multi-resolution analysis. I'll get to that later on. I just want to focus on the Haar setup for now. Okay, now, if you're given an x in L2, you can think about projecting at, yes, Manish.
Is that V not supposed to be VK?
Yeah, because I was talking about VKs, right? Yep, thank you. All right, so if you're given an x in L2, you can think about projecting it on each of these v's, right? You project it on v sub minus 1, you get something. You project it on v0, you get something else. You project it on v1, you get something else, and so on and so on. Those things are going to approach x as k goes to infinity. So I'm going to let projection sub k, or projection of x onto v sub k, be the orthogonal projection of x onto v sub k. And that's for all k in the integers. Here's a fact. Well, first, how do we think of the projection of x onto v sub k? The projection of x onto v sub k is in v sub k, therefore it's a step function, and the step function step lengths are 2 to the minus k. So note, proj of x onto v sub k is a step function with steps of length 2 to the minus k. That approximates x. Approximating x as well as possible among all such step functions. So better than any other such step function. That's what orthogonal projections are. They're the vector in the subspace closest to the thing you're projecting. And you can think of proj of x onto vk as a quote-unquote k resolution or resolution k or quote-unquote resolution 2 to the minus k, however you want to think of it, approximation of x. Thus, as k grows, you get a higher resolution approximation of x. That's why I think of resolution k is probably better. And as k goes to infinity, it turns out that the limit of these things is, as we might want it to be, x. And that follows from the fact that the vk's in some sense span L2. All right, so those are the generalities about like what's happening with these Haar things. And let me just see if there's anything else I want to say before I move on to this. Oh yeah. I already noted that for each of these k's, the phi n comma k are an orthonormal basis for vk. But if you look at one particular containment, vk to vk plus 1, so let's zero in on vk contained in vk plus 1. So you have vk, it's a subspace of vk plus 1. What do you have to add to vk to get vk plus 1? We haven't talked in this class about something called the orthogonal complement. You talked about that, I think, in linear algebra. But the idea is that to get vk plus 1 from vk, you have to throw in enough other stuff to span vk. So what do we need? What other stuff do we need? Do we have to quote unquote add to vk to get vk plus 1? Well, it turns out, and this is another thing you can put, there's an awful lot of turns outs today, but these are not difficult things to show. It turns out that to get v plus k plus 1 from vk, you end up having to throw in the scale k wavelets of various shifts. So first, let's look at v0 contained in v1. It turns out that the set of all psi n0 such that n is in the integers, all of which are orthogonal to v0, form an orthonormal basis for what you need to tack on to V0 to get V1. So these are enough to span the quote-unquote difference between V0 and V1. And if you want to be technical about it, let me tell you the technical phrase that goes along with this. And this isn't something I'm expecting you to internalize necessarily. Has any of you ever had a course from Andy Ruina before? Yeah? Okay, so then this wouldn't entertain you, so I won't. It would entertain you maybe, but not. No, I just ran into him a few minutes ago, and he was extolling the virtues of this kind of blue cloth for erasing blackboards as opposed to erasers. And I remember these cloths from last spring in Olin 165. And all I know is that they give me the creeps to have them in my hand. They have this, you know how things catch on your skin or something like super synthetic fibers? That's, yeah. But he was saying, these are so great, they're so much better than erasers, you know. Anyway, that's what professors talk about, I guess. Okay, so anyway, technically, what am I saying? And you can look this up. The set of all psi n0 as n runs over the integers is a complete orthonormal set in what's called the orthogonal complement not complement of V0 in V1. Essentially what you do is you think of V1 as being a big ambient space, V0 as being a subspace in there, and the orthogonal complement is the subspace of all things in V1 orthogonal to V0. And it turns out that the 0 resolution wavelets are a complete orthonormal set for that. And in fact, for every k, so for every resolution k, the psi nk's as n runs over the integers is enough to get you vk plus 1 from vk. So quote unquote spans the quote unquote difference between vk and vk plus 1. And if you want to be technical, you could say that the set of all psi n k as n runs over the integers is a complete orthonormal set in the orthogonal complement of vk and vk plus 1. So if you look at this nested decomposition of L2, what it says is that each time you go up one step, you throw in the resolution wavelets for that step, and that'll give you an orthonormal basis for all of L2. Okay, now there's a lot of orthonormal bases going around here. I admit that, and I'm not apologetic about it. That's the way it works in Hilbert spaces. I guess now's a good time to take a 3-minute break, and we're all ready to talk about the speedy computation thing that Zach left so he won't get to see. Haha. So. I hope that when this doesn't heal, the doctor doesn't say to me, have you been writing on the board? You know, like, that's the worst thing you could do for a tough fracture of the distal phalanx of your right thumb. Can't you use your left hand? No. All right. So anyway, I've been throwing a lot of stuff at you. And I'm sorry about that. but that's the way it goes. Okay, now there's a couple of key relations between the fees and the size and stuff for the Haar system. So for the Haar system, we have some key relations. And these are the ones that make for the computational advantages of the so-called fast wavelet transform. Okay, first of all, let me graph up here. Remember, this is phi. Phi of t versus t, and this is psi of t versus t. Now, clearly, those are related in a certain sense. First key relation says the following. It says that phi, which is the same as phi 0, 0, is equal to scale 2 of phi plus scale 2 of shift 1 of phi. What is scale 2 of phi? Scale 2 of phi is this. So it's like the first half of phi. Scale 2 of shift 1 of phi is this, it turns out. It's the other half of phi. So if you, the bottom line is I'm expressing, and this, by the way, is the same as the square root of 2 times phi 0, 2, 0, 1 plus the square root of 2 times phi 1, 1. Or is it 1 over square root of 2? Let me think about it. I think it's 1 over square root of 2. So I'm going to write it 2 to the minus 1 half. Okay, so that's a relationship between the phi at 0, 0 and the phi at 0, 1 and the phi at 1, 1. If you shift this by n, similarly, this generalizes. Let me just tell you what it generalizes to. If you play around with shift sub n and scale sub 2 to the k, using that relationship I had written on the left last time, which was that scale sub 2 to the k shift n is the same as shift n times 2 to the minus k scale 2 to the k. Playing around with those things, you discover the following. And I want to get this right. That phi nk equals 2 to the minus 1 half phi n, or phi 2n comma k plus 1 plus 2 to the minus 1 half phi sub 2n plus 1 comma k plus 1 for all n and k. And I'm going to put a big circle around that because that's an important relationship. Now, why is it important? Well, it's important because it expresses the next lower resolution phis in terms of 2 of the next higher resolution phis. And I have no reason for you to expect you to understand why that's important. It turns out that it's going to give us a nice recursion for figuring out wavelet coefficients. So be patient on that. Similarly, you could play the same game with phis, with psis, I mean. First, note that psi itself, which is psi 0, 0 in the psi nk notation, is equal to what? It's equal to scale 2 of phi minus scale 2 of shift 1 of phi. Only difference there, we had a plus. Here we have a minus. And again, that's the same as 2 to the minus 1/2 phi 0, 1 minus 2 to the minus 1/2 phi 1, 1. And if you play around with shift sub n, scale sub 2 to the k, using that relationship of how to reverse them, you get a relation like this, but for the size. So this generalizes to psi nk is equal to 2 to the minus 1/2 phi 2n comma k plus 1 minus 2 to the minus 1/2 phi 2n plus 1 comma k plus 1 for all n and k. So put a big circle around that one. All right, so qualitatively, what are these circled equations? Qualitatively, what we have here is we have formulas for the scale k, or resolution k, wavelets and scaling functions. So the resolution k, scaling, and wavelet things, whatever you want to call them, I'll call them functions, in terms of the resolution k plus 1. Ones. So it's a recursion relation. It gives us the resolution k stuff as in terms of the resolution k plus 1 stuff. But it's even better than that, because each of these formulas for a psi nk or phi nk involves only 2 of the things from resolution k plus 1. And there are different 2 for every one of those, and so we can compute all these things in parallel. That's a really nice thing. And this is very closely related to what happens when we talk about the FFT, but I don't want to dwell on that too much. All right, so suppose we have a signal x in L2 and we want to compute its wavelet coefficients. How do people do that in practice? We have all this machinery and absolutely no idea how to use it. Well, maybe you guys know, maybe you're prescient or something, but I haven't told you how we're going to use all this machinery. Yeah, David. For the size? Because the psi is that thing on the bottom there. And to get this thing, you have to take, instead of taking the sum of these two guys, you take this one minus that one. Got it? Yep. Okay, so how do we apply all this stuff? what I'm going to tell you about is what people call the fast wavelet transform, at least in the context of a Haar wavelet system. So here's a description of the fast, and I'll put in parentheses Haar, because those are the ones we're talking about, wavelet transform. And it goes something like this. All right, starting point. You have a signal X in L2. And you can assume it's decent if you want, whatever. What we really wish we could find is all the wavelet coefficients for X. But we're not. We're not going to find all those wavelet coefficients. We're only going to find some of them. And in fact, we're not even going to find them exactly. We're going to find them approximately. Okay, so start with X in L2. We'd really like to have all the wavelet coefficients, set of all X, inner product with psi nk, for all n and k in the integers. But instead, we're going to shoot a little lower. So we'll only go for part of that. So only go for part of that set. How do we only go for part of that set? First of all, we set an upper bound on the resolution we care about. And I'm going to call that upper bound, I thought about calling it K bar, but there's too many bars and subs and all that stuff, so I'm just going to call it L, capital L. So what we're going to do is we're going to start by picking L. And generally, L is going to be bigger than 0. So that, at least as far as we're concerned, all the quote-unquote interesting features of X have resolution at most L. Quote unquote. And what I mean by that is, i.e., so that projection of X onto V sub L is, as far as we're concerned, a decent, no, don't use the word decent because that has a technical meaning, is a good approximation for our purposes of X. Now, what would be an example of setting an upper bound on the interesting features, upper bound on the resolution? How does one arrive at such a thing? Suppose X is an audio signal, say, or any kind of signal that has a spectrum. Then if X is band limited, we know that if we sample X faster than twice the bandwidth, well, we'll learn that later in the class, but you learned that in EC 2200, you get as much information as you possibly can about X. So in a sense, all the interesting features of a band-limited signal that's band-limited to within some omega sub m are going to be of scale on the order of twice the bandwidth, or log of twice the bandwidth to the base 2. So that's how we pick our L. So for example, for a band-limited X, you might pick L, so 2 to the L is on the order of 2 times omega m, or omega max. Okay? All right, so that's just one example of how you might do it. But anyway, you have to start somewhere or end somewhere. You have to not go for all the wavelet coefficients. You have to say, okay, I'm just going to get the wavelet coefficients out to resolution capital L. Then what do you do? Then you initialize your algorithm with estimates of the scale L fees and the scale L size. How does that go? Or just scale L fees is all we need. So next you initialize your computation with approximations for phi sub n comma L as n runs over the integers. Now, what are those approximations going to be? How do they arise? If you think of phi sub nl is a teeny little step function. It's of width 2 to the minus L, height 2 to the L. It happens right around time n times 2 to the minus L. So what you're doing essentially is almost sampling the signal at that point. You're computing the average value of the signal over a very tiny interval, 2 to the minus L length, near the point time n times 2 to the minus L. So in practice what happens is, what you do is you get these things by sampling x every n times 2 to the minus L, or every 2 to the minus L seconds, starting at time 0, and setting your estimate phi sub nl equal to x of n times 2 to the minus L for all n in the integers. Okay, so say you have a music file, or say you have a music signal. You sample it at 44.1 kilohertz or whatever, some power of 2 kilohertz, or whatever. And you initialize your algorithm by setting all the phi sub nl's to be equal to the values of x at the appropriate sample times, the times at which the phi sub nl's are concentrated. Then what do? Now you have all the phi sub nl's. You use the circle equations to compute phi sub n L minus 1 and psi sub n L minus 1. So now you recurse. Is that a verb?
Yeah.
To recurse?
I think so. Yeah.
What's that? So in German it would be rekursen, and past participle would be gerekurst. No, anyway. Now you recurse using the circle equations to get the x, psi, and k for all k less than or equal or less than L for as long as you want to go. And you can stop. Usually what happens is that when k gets small enough, these coefficients start getting tinier and tinier and tinier. So generally, the x, psi, and k get small as k goes down. So you just decide when you want to stop. Decide when you want to stop. So how do we recurse on these things? Well, you take the inner product of x with both sides of the equations. The idea is the recursion looks like this. X inner product with phi nk is equal to 2 to the minus 1/2. X inner product with phi 2n comma k plus 1 plus 2 to the minus half. X inner product with phi 2n k 2n plus 1, k plus 1, and x with psi nk, those are the things you really want, is equal to the difference of these two. And you start with k plus 1 equals L, using x of n times 2 to the minus L for this thing and this thing. Except in one case you're going to have 2n times 2 to the minus L, and the other was 2n plus 1 times 2 to the minus L. Okay? So that's how you get the wavelet coefficients. Now, like I said earlier, this is set up ideally almost for computation because you can compute them in parallel. You can do all those computations in parallel. And the way that the next higher ones and the next lower ones are related is in a nice organized way. And people have all kinds of cool characterizations of this in terms of filter banks and whatever. There's a book someone wrote called Wavelets and Filter Banks. Gilbert Strang, he also wrote a famous linear algebra book. You might have used that in linear algebra. Did you use that? Gilbert Strang? Or Strang and some weird name?
I don't think so. I think the arts math class.
The arts math. No. Okay, well, anyway, what do you do after you've done this? You do it for a really long time, or a really long number of resolutions. And you end up with a zillion coefficients. The computation is efficient, but you're building up data pretty fast. So the recursion, the recursion is set up nicely. Boy, I hope this thumb gets better quick. You can see that the others, it's turning more purple from giving this class. But anyway, the recursion is set up nicely for parallel computation, etc., etc., similar to the FFT. So it's a lot like the FFT, which we'll learn about in a week or so, 2 weeks. But it still is going to generate a lot of coefficients. Namely, the set of all x, psi, and k, such that k is less than or equal to L for a while, at least. Okay, so once you've quit doing this, once you've reached a, say, like a lower k value you want to stop at, you have this big list of coefficients. What do? You throw away a bunch of them. You throw away the ones that are below a certain level. So once you have all these data, so once you have reams of wavelet coefficients for x, what you do is you decide how low a coefficient you're going to keep. And below that, you throw all the rest of them away. So you throw it out, you compress, and this basically is how MP3 works. You compress by throwing away, throwing out all the coefficients below a certain value. And that's how you do lossy data compression on wavelet stuff, wavelet coefficient arrays, to get, say, MP3 from a CD standard, right? Something like that. Like a CD, what is the CD standard for music? You sample every 44.1 kilohertz, and you have this huge data file of 8-bit approximations to, 256 levels, blah, 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 blah. You take those and you go through this. You do a discrete wavelet transform on those and essentially throw out all the coefficients with a certain value, and that gives you an MP3 file, which is way lower in terms of how much data is in there. So the sort of canonical example is, for example, CD becoming an MP3. And I'm really giving you a sketchy description here of what's going on. And you may say, well, wait a minute now. We had Fourier series, right? We had coefficients. Why not just take, say, if you're trying to approximate a periodic signal, why not take the Fourier series and just throw away all the coefficients below, say, 10 to the minus 3 or 10 to the minus 59? Well, you probably can't even resolve that. And the answer is that it turns out that Fourier does a much worse job of approximating a signal when you throw away coefficients below a certain level than the wavelets do. The wavelets do a much better job because what you're doing is the wavelets, like for example, what if I take a signal that has a musical signal has lots of silence somewhere, right? Well, all the wavelet coefficients for n values, nk values for which n times 2 to the minus k is in the silent zone are going to be really low. So I won't even bother carrying them along on my MP3, right? Like by default, they're 0. And you do a much better job. And if you have like a Fourier approximation of that, you're going to have Gibbs phenomena near the edges and all that. And so it does a lot worse job. And so basically what I'm trying to say here is that, and this, by the way, we're only talking about the Haar system here. The more complicated wavelet systems, you have more complicated recursion relations. Maybe I'll talk about that briefly at the beginning of class next time. But what I'm trying to say here is it turns out this quote-unquote compression by tossing small wavelet coefficients is much better than quote-unquote compression by tossing small Fourier series or Fourier transform coefficients. So I'll put coefficients in quotes here to mean, roughly speaking, pieces of a continuous spectrum or coefficients in a Fourier series that are below a certain value in terms of approximating the signal. And especially in terms of approximating signals in ways that mesh well with our perceptions, either audio or visual perceptions, it turns out. And Professor Hamami, who unfortunately isn't at Cornell anymore, knows an awful lot about the way that wavelets are better for vision than Fourier. So anyway, maybe we'll talk a little more about the general version of this next time, maybe not. I'll see you then.